There you go. See if it works. Thank you.
We stand at the apex of digital transformation. We see a world where everything computes. A situation where apps give rise to intelligent spaces. Spaces that see, hear, and serve. Reality is being sensed. Machines are learning, and decisions are being made with increasing autonomy, enabling a safer, more efficient, and better connected world. We see hybrid IT, where businesses can learn the facts of their environment from multiple dimensions in real time and can reliably analyze that data in the right way to compute the connections that educate us, that elevate us across all industries, creating billions of new touchpoints and new paradigms where memory-driven computing shapes the future. Hewlett-Packard Enterprise creates the right mix for your business, from core to cloud to edge, so that everything computes.
There you go. So we'll go back to where I left everything. So in that convergence, between the various disciplines that are supported by HPC is also generating a lot of data. So we see an explosive growth of data, and that's interesting because I think the gentleman presenting the Western Digital presentation mentioned 165 zettabytes of data. As you can see on my slide, I'm seeing only 40 zettabytes. 1 zettabyte is 1 sextillion, by the way. I just looked it up a bit earlier on. And that's really generated by the deluge or the explosion of connected devices that we've got, whether it is, tablets, phones, connected clothes, obviously autonomous vehicles, et cetera, et cetera, et cetera. And for us, the underlying infrastructure or hardware is just basically an enabler. The value really resides in the data that you generate and what do you do out of that data. I call that a data tsunami. We've heard data deluge, but it's obviously today what's really driving the industry. It's how do you basically unleash outcomes and you unleash value outside of all the data being generated, whether it is, in enterprise, in research education, in science. It becomes somewhat irrelevant if you look at the hardware or the infrastructure that you could deploy, if you don't have the ability basically to pre-process, to post-process, and to analyze that data in real time. And we need answers fast. The value of the data tends to decrease with time. So we live in an impatient world where you've got to have the ability to very, very quickly analyze that data and understand, what it means for your business, what it means in terms of science. We want to go quickly to understand how a cyclone, where a cyclone might hit, for example. We want to be able, with autonomous vehicles and robotics, to be able in real time to get the car to steer away if there is a pothole on the road, et cetera, et cetera, et cetera. So all of that is pretty clear when you look at things like the number of Google search that are being done on a per day basis. There's 3.5 billion Google search. There's roughly 400 hours of YouTube video being added up on YouTube every hour. There is 3.5 million Facebook messages being posted every second. It's amazing how the world has changed and has become very, very data-centric. So let's take the example of autonomous vehicle. That's the Tesla car. If you look at the number of data being generated per hour today by a Tesla car, it's around 4 terabytes. That's for one car. There was the CTO of Xilinx, the FPGA company, that a few weeks back mentioned that in order to process all of that data, you would literally need 300 teraflops of onboard processing power, which is, a supercomputer. I know many sites that don't have 300 teraflops, of CPU processing. The interesting thing is once you've processed all of that and you're at the edge, how do you move that back to the core and to a central facility, whether it is in the cloud or it is in a on-site, on-premise data center. And you realize that we've got a challenge with networking. So we've got our friends at Mellanox here that hopefully will fix that for us. But it is expected that we'll need 25 to 40 gigabytes per second to just basically manage all of the data being generated by one single car. I believe that in 2020, there should be around 10 million autonomous car potentially on the road. Whether or not they will be fully autonomous, would be a different story. Obviously, there's a lot going on in terms of governance to get the cars, on the road. But it is mind-boggling to just look at the numbers. And that's why for us HPC matters, because HPC, that used to be the turf of universities, research and education side, has become very, very pervasive. And it is really going into all areas of industries because we need more and more of that compute power, more and more of that ability, to process large amount of data in real time. So now once you've got all of that data, as I've mentioned earlier, so you take a car, with 10 million cars, it would be 40,000 petabytes per day of data that needs to be analyzed and streamed in real time. Today, Facebook, there's 4 petabytes of messages, being posted on a daily basis. And Walmart last year was managing around 40 petabytes of data through their various databases internally. All of that has to be sort of coalesced and looked at, in parallel to sort of make sense and look at patterns on how you can unleash, more value out of that data. So you want to turn it into insight. You want obviously, to be able to make better decisions in terms of take for Walmart, your supply chain, having the ability in real time to understand what goes through the till and how can I line up the supply chain. For example, on a hot day, we realize that the ice creams are flying off the shelves. Make sure that within 1 or 2 hours, we start restocking. And potentially it's going to be a hot weekend. So let's send, an emailer campaign to our clients with a promotion on ice cream to get more people in, et cetera, et cetera. And part of that is actually being improved via things like deep learning and artificial intelligence, where now we've got the ability to look at those massive data sets and develop algorithms that makes us understand better how every type of data can be synthesized together, to obviously unleash more insight and commercial results or scientific results or you name it. So that's why we've termed, or our CTO has termed data as being the new IP in today's digital world. We feel like this is the most valuable asset of any organization. whether commercial or not. It's fairly easy to get the right level of compute engine. We talk about exascale. Anyone can deploy an exascale system today. You just need basically a few $1 billion. You need a nuclear power plant, and make sure that you haven't signed, the Paris Agreement, and you're fine. So it's how do you make it sustainable, I guess. But again, the technology and the hardware is available today. We just want to make it sustainable from a real estate perspective and from a power and cooling perspective, and obviously more affordable. We've got high-performance storage that works pretty well. There's different types of parallel file system technologies that help us move that data, fairly quickly, especially with new NVMe and flash-based technology. And you've got long-term storage as well to sort of secure the data at a fairly reasonable price. Tape is not dead. Even though I kept hearing that in the 20-odd years I've been working in the industry. I've heard that we'll soon have 35, 40 terabyte drives anyway. So we've got the means today of storing and archiving that data in the long term and make sure that we can revisit the data at any time. The question mark is, we've got all the various components, but how does that sort of gel together? And that's sort of my one HP only product reference. We've got a software called DMF, which is an HSM software that basically helps making sure that we can capture that data and move it between all the various components of a technical computing deployment that we've seen just now, and make sure we keep that in the long term and have the ability to access it in real time, to recall it in real time, to analyze it in real time. I should actually copyright data for life. That's my finding. I like that. Okay. So I'm getting to the end of it, so I'm going to give you a bit of time. I've got another video that is pretty close to my heart. Obviously, we are close to Perth. Perth, for the ones that are not familiar with the city, has become one of the top 5 radio astronomy centers in the world, thanks to ICRA, UWA, the Posey Center, the Murchison, and the Australian Square Kilometre Array Pathfinder. So I'll just fire off. It's a bit of a longer video. It's like 5 minutes, and I'll tell you why it's close to my heart later on. But let's go. And it didn't work. Beautiful. Where is my technician? I might get back some of that time I was looking at giving you, but there you go.
Being here at the Maths faculty in Cambridge with some of the most famous physicists in the world is absolutely amazing. Every day I come here and I see those amazing buildings. Somehow it sort of radiates knowledge.
No matter what you want to think about, you've got someone who's a world expert to talk to.
Yeah, Stephen Hawking is definitely a draw. Whenever he comes in, it never gets old. It's always quite exciting. He comes into the department.
Of course, it's been amazing to see Stephen Hawking close up over so many years. But more than that, of course, he's a singular individual. He's an inspiration to everyone. One of his mottos is never give up.
The biggest and most interesting thing is the whole universe. How does the whole universe work? How does it really fit together? What's the sort of clockwork behind it that makes it run the way it does?
Curiosity is essential to being human. From the dawn of humanity, we've looked up at the stars and wondered about the universe around us. My Cosmos group is working to understand how space and time work from before the first trillions of a second after the Big Bang up to today, 14 billion years later.
The Cosmos Group focuses on the most extreme events in the universe, when the basic fabric of space and time is shaken up.
We are searching for tiny signatures in huge data sets to find clues that will unlock the secrets of the early universe and of black holes.
Without computers, what we do now would be impossible. Now, the data sets are getting so big, there's so much information. Some of these data sets are billions and billions of galaxies.
In both cosmology and in relativity, we face this deluge of new data that presents us with a lot of challenges computationally. So we were pleased when HPE was able to bring many more resources to in-memory computing.
In-memory computing definitely helps us to do this a lot easier because it enables us to test our algorithms quickly and easily.
I mean, it's the perfect system for me. It's almost designed specifically for my work.
It's so flexible. It allows you to ingest very large data sets and act on them immediately. It allows you to try out new ideas, new algorithms, to innovate and develop your codes faster. So it gives us a competitive edge in a very fast-moving field.
Academia is a fiercely competitive industry. For you to stay ahead of everyone else, you've got to be pushing the boundaries. Having the right architecture behind you, the right systems behind you, is a really key part of that.
We work hand in hand with the scientists, getting a new system to help them even further in their scientific endeavors is just fantastic.
The first ever direct detection of gravitational waves announced last year caught me by surprise, because I did not expect it so soon. The signal found by the LIGO experiment of two merging black holes marks the dawn of a new era of gravitational wave astronomy.
It was really big news. Yeah, it opens up a completely new field.
A billion years ago, two black holes in a distant galaxy, they merged together. The gravitational effect of this was so strong that it actually created these ripples in space-time.
The gravitational waves traveled through the universe, and we measured those gravitational waves in our detectors, and we could predict the signal precisely. We've done very theoretical research for a very long time, and we can now suddenly take all of our theories, take all of our computer simulations, etc., and look at the data on the fly and compare them to reality. I mean, this is what we want to do as physicists.
Within memory computing, we can keep up with the flood of new data, and we can keep ahead because we are free to innovate.
It allows us to do bigger simulations, more accurate simulations, and to really test our theory at a tighter and tighter level. So that's where shared memory computing really is the key advantage for us.
Whip up a code, no matter how weird or complicated the idea is, you don't have to worry about how much memory you use doing that, and you get some idea of whether your idea even works.
It's great because we can get students who, with a minimal amount of programming introduction, can actually use the system and do large-scale problems and get solutions.
The field is moving too fast to wait until we are all advanced programmers.
We want to be focusing on the science and on the discovery and testing our ideas.
The universe really is the ultimate laboratory for testing our ambitious ideas about the fundamental building blocks of matter and of space and time.
There's not that many huge mysteries left in science out there, and we're really living in a time where we should get them.
This high-precision science and our complex theories will only be able to confront each other using powerful computers. Without supercomputers, we would just be philosophers.
There you go. You won't get the logo. So the reason why that video is close to my heart, it's I was lucky enough to meet up with Professor Hawking early on in my career in the late 90s when I was living in the UK. But also because the message that is given there is sort of well aligned, you know, with what I've just presented, where there's a massive amount of data that needs to be computed, and technology and differentiated technology can really help us, you know, accelerate and unleash scientific outcome and results at a quicker pace. So I think it's a great message as well. Now, one last slide before I wrap up. there's an initiative that HP has worked on with NASA, and it's to send a supercomputer, a small one, obviously, you can see it on the right-hand side, on the ISS. And it might seem trivial, but I think it's quite interesting because forget about the machine itself. If you understand how things work with NASA, in the past, they used to have to ruggedize anything they would send on the space station. And it would take a good 2 years to 3 years before they would get all the certification in place. And basically, by the time you send something there, it would be obsolete, as simple as that. It would cost a fortune. And that didn't make much sense. So HP approached NASA and said, well, why don't we try, to use COTS equipment and send it over there? And we did. And that supercomputer has been basically in production for almost a year now. And we've had, the usual sort of hiccups where it's only powered via solar panel, and one day, the whole thing went down, but it's been running fine. And we've just been able to demonstrate that you don't necessarily have to ruggedize your equipment. But most of all, we've been able to demonstrate that potentially with the mission to Mars that NASA is looking at, we'll have the ability, to do that computing at the edge very far from Earth, potentially in real time. So someone asked me, my colleague there, okay, but when you go to Mars, you're going to have a network bandwidth issue. Because the signal, from Earth to Mars takes 20 minutes, and then it takes an extra 20 minutes to come back, so that's 40 minutes. And the idea is to do it in real time, so if there is a problem when we've got human on Mars, they can communicate with Earth. And I've said to him, that's a very good question. You've got many people from Mellanox, check with them how they can fix that for you. And on this, I will finish off with that great saying or statement from Stephen Hawking: without supercomputers, we would just be philosophers. Thank you.